Welcome to the explainer. Sometimes in math, one single idea can unlock a whole new world. Today, that's exactly what we're going to do. We're going to tackle the derivatives of exponential and logarithmic functions by going on a hunt for one magic number. Seriously, this one number is the key to everything we're about to cover. So, here's the plan. First, we're going to see why our usual rules just don't work here. Then, we'll go on that hunt for the special number e. After that, we'll use e to crack the code for natural log derivatives. From there, we'll solve for any base, and we'll finish up with a really cool trick called logarithmic differentiation. Sound good? Let's get into it. Okay, first up, the challenge. Let's look at a type of function that kind of breaks one of the very first rules you learn in calculus. So you know how to handle something like x squared, right? It's the power rule. Classic stuff. Bring the 2 down, subtract 1 from the exponent, boom, done. But what happens when we flip it? What if the variable x is in the exponent, like 2 to the power of x? Suddenly, the power rule is useless. It just doesn't apply. We're stuck. So we need a whole new approach. All right, so when in doubt, we go back to the basics, right? Let's use the limit definition of the derivative. Now, I won't walk you through all the algebra here, but when you work it out, something really amazing happens. The derivative of any exponential function, like b to the x, turns out to be, well, it's just the original function, b to the x, times some constant. And what is that constant? It's the slope of the function right at the very beginning, at x equals 0. How cool is that? So think about what this means. Our whole big problem just got a lot smaller. It all boils down to one single question. What is the slope of our function right at x equals 0? If we can figure that out, we've cracked the code for all exponential functions. This leads us to a really fun idea, a hunt for the perfect number. What if we could find a base that makes this whole derivative thing, well, super simple? I mean, what's the simplest possible constant we could hope for? How about 1? Imagine if we could find a base b, where the slope at x equals 0 is exactly 1. Then the derivative of b to the x would just be b to the x times 1. The function would literally be its own derivative. I mean, could a number like that even exist? Well, it turns out it does. And this table shows you how mathematicians basically zeroed in on it. They tried a base of 2, and the slope at 0 was too small, about 0.69. Then they tried a base of 3, and whoops, too big, about 1.1. So they knew the magic number had to be somewhere in between. And look what happens. As they get closer and closer, testing 2.7, then 2.718, they get incredibly close to a slope of 1. It looks like the sweet spot is right between 2.7182 and 2.7183. And here it is. This graph shows it perfectly. That magic number, which we call e, gives us the function e to the x. And if you look at the tangent line right at x equals 0, its slope is exactly 1. It's the perfect base we were searching for. And this gives us our first huge breakthrough. The natural exponential function, e to the x, is special. It's the only exponential function whose tangent line at x equals 0 has a slope of 1. And that means its derivative is just e to the x. It doesn't change. This function is its own rate of change. That is a wild and incredibly important idea in math. Okay, so we've unlocked exx. Now, what about its inverse? Let's use what we've just found to tackle the derivative of the natural logarithm. The key here, as the quote says, is that we can use the inverse relationship. We don't have to go all the way back to the limit definition again. Nope. We can use a really slick trick called implicit differentiation. So here's how it works. We start with y equals ln of x. Because they're inverses, we can just rewrite that as e's to the y equals x. Now we differentiate both sides. On the left, we use the chain rule, which gives us e's to the y times dy dx. On the right, the derivative of x is just 1. Then we just solve for dy dx and substitute back, and what we're left with is another just beautiful, simple answer. There you have it. The derivative of the natural log of x is simply 1 over x. That's it. Another incredibly elegant rule, and it all came from our hunt for that magic number, e. All right, we've got the derivatives for the natural guys, e to the x and ln x. Now we can finally go back to our very first question and solve this thing for any base, not just e. And the tool that lets us do this is the change of base formula. You've probably seen this before. It's basically a way to translate any log or exponential into the language of ln x and ex. And since we know how to handle those, we're good to go. This formula is the bridge that connects it all. And check out the result. When you compare the general rules to the natural ones, they're almost the same. The derivative of b to the x is just b to the x times a little something extra, the natural log of b. And the derivative of log b of x is almost 1 over x, but it's got that ln of b in the denominator. So that mystery constant we found way back at the beginning, that b prime of 0, it was the natural log of the base the whole time.
Okay, now for the grand finale. We're going to take everything we've learned and build a kind of secret weapon, a technique for solving derivatives that look, frankly, impossible.
So what about a function like x to the power of x? Just think about that for a second. The base is a variable, so the exponential rule doesn't work, but the exponent is also a variable, so the power rule doesn't work either. We're totally stuck. Or are we? This is where our new trick, logarithmic differentiation, comes in to save the day.
The strategy is actually pretty genius. Step 1, you take the natural log of both sides. Why? Because logs have these amazing properties that let you turn multiplication into addition and, crucially, bring exponents down as multipliers. Suddenly, a horrible-looking problem becomes a much simpler one. After that, you just differentiate implicitly like we did before, solve for dy dx, and swap the original function back in at the end. It's an incredible problem-solving tool.
So let's just pull this all together. It all came back to finding that one special number, e, the unique base where the slope at the start is exactly 1. That simple fact gave us d dx of ex equals ex. From there, we got the derivative of its inverse, ln of x, which is 1 over x. And with those two pieces, we could figure out the rules for any base. And to top it all off, those tools gave us logarithmic differentiation, this awesome trick for tackling super complex functions. You know, we started with a really simple question. How do we differentiate 2 to the x? And look where we ended up. We now have a tool that can handle something as wild as x to the x. It just goes to show you how one beautiful, simple idea in math can unlock solutions to problems you never even thought you could ask. So what other impossible-looking functions can you solve now? Thanks for joining me.